In section 4.2, we're now going to take a closer look at how the behavior of a derivative of a function affects the shape of its graph. And by understanding this, we'll be able to use critical numbers of a function to find all of its local extrema. So that's where we're headed. So I'll start by asking you to just consider the following picture. Okay, so I've written here, consider the graph of a function f defined on the closed interval a to d. So let's draw a picture. So we've got some graph of a function f. Okay, now I'm just going to draw a segment of a curve just to illustrate a point. And I'm just highlighting 4 points of interest. Really, you can see I've made a point of really emphasizing the endpoints of the curve segment as well as the local max and the local min. So let me label those points now on the x value, or on the x-axis. So I'll label this as A, this as B, C, and D. Now, I've written out some space for some observations down here, which we're going to fill in now. The first observation I want to make is that look at what happens if I take a point between A and B, and then like on the x-axis, and then I go up and I look and find the corresponding point on the curve. So let's say I took a point here, just at random, between A and B. Now there's a corresponding point on the curve right here. What's the slope of the tangent line to the graph at that point? Well, you're not going to know exactly, but maybe I should rephrase the question. What can you say about it? Can you say anything at all? Well, based on the picture, you can, at the very least, you can say that the slope of that tangent line is positive, right? Because it's pointing upward and not downward. And would that be true if I moved this a little bit to the left or a little bit to the right, but I didn't go past B, like I stayed within this range? Would that still be the case? And the answer is yes. And really, it has to do with the fact that as you move to the right from A and move towards B, the corresponding points on the graph, their y values go up. So as the x values increase, the y values increase between these points. Or in other words, the function's increasing, really is a nicer way to say that. But here's the observation and the way I want to write it down. For any point x in the open interval a to b, the derivative of the function f at the point x is positive. And really that's what that tells you that the function is increasing on the open interval a to b. On this interval, the function is increasing. Okay, what about at b exactly? What if you actually plug in the point b exactly? If I look at b, then I'm going to go up to this maximum here. And we've kind of already talked about this, but let's just remind ourselves what happens at a local maximum. Well, the slope of the tangent line is going to be 0. The tangent line is going to be completely flat. So that's our second observation. This one's a little quicker to say. F prime of b is actually equal to 0. Okay, let's pick a point in between B and C now. And again, I'm just going to kind of pick it more or less at random. But the idea is whatever we observe about this point, you'll probably be able to see that we can easily generalize that to any point that falls strictly between B and C. So what's the corresponding point on the curve? Well, there's a point here on the graph. What's the slope of that tangent line? Can we say anything about it? Well, if I draw the sketch, it's going to look something like that. Right, we're getting lots of lines on this graph, so it's going to start to become a mess soon, unfortunately, but I'll do my best to kind of keep it organized. But if I draw the tangent line to the graph at this point, which corresponds to this value, you can see that this tangent line has a downward slope, right? It's got a negative slope. And that really comes from the fact that as the x values start at B and increase towards C, the corresponding points on the graph, their y values decrease. So we're going to have an observation that's similar to the first one here, but a little bit different. So for any x in the open interval b to c, our function's derivative is negative at that point. Okay, then what happens at the point C? Right at the point C, that's where we have a local minimum. So just like with the local maximum, our tangent line is going to end up being flat at that point. So it has a slope of 0. So we can add that in. Our fourth observation will say that f prime of c is equal to 0. And then lastly, what happens between c and d? If I pick a point between c and d, not including either endpoint, something strictly between c and d, well, the corresponding point on the graph, if I draw the tangent line, it's going to have a positive slope again. And really that comes from the fact that as the x values increase, so do the y values. The function is increasing from c to d, just like it was from a to b. So our last observation will be for any x in the open interval c to d, f prime of x is positive because the slope of that tangent line is positive. Okay, and this is really the motivation for the following test, which I'm about to write down, which is called the increasing-decreasing test. So the way it works is as follows. Let I be any interval. It could be closed, but really you should think of it as an open interval because that's the way you're typically going to apply it in this course. But it says the following: if f prime of x is greater than 0 on I, meaning that for every point x in the interval I, if you plug it into the derivative of f, you get a positive number. That's what it means for f prime of x to be greater than 0 on I. It means it's greater than 0 for every x value that falls in this interval. And if that's the case, then f is increasing on that interval, just like we saw above. This test just tells you that that generalizes to other functions. Because it seems to be clear in the case of this picture that I drew, but this is a specific function. Even though I didn't write it down in terms of a rule, this is still a very specific curve. But the increasing-decreasing test is just telling you that this is going to happen in general as well. And then the other half of the statement just says the analogous result for a negative derivative. If your function's derivative is negative for every point x in that interval, then f is decreasing on that interval. Okay, so really with this information, the derivative tells you exactly when the function's increasing or decreasing. We've kind of made a vague comment about that earlier, but we didn't actually apply it, so now we're actually going to put this to use. And let's start with this example. So we've got a function f. It's defined by this polynomial, and we want to know when is this function increasing or decreasing. Well, we need to figure out when the derivative is positive and when the derivative is negative. On which intervals I is the derivative positive, because that's going to tell you where the function's increasing, and on which intervals I is the function's derivative negative. That's going to tell you where the function's decreasing. So we're going to start by, well, you could probably guess, we're going to start by finding the derivative, because that's what we need to analyze here. So let's start with that. So our derivative, f prime of x, we'll just go term by term. Differentiate the 3x to the 4, and you get 12x cubed. Differentiate the 4x cubed, and you're going to get, well, bring down the 3 and multiply it onto the 4, you're going to get 12. So it'll be 12x squared. So minus 12x squared, and when you differentiate 12x squared, you're going to get 24x. And then the derivative of 5 is just 0. So this is our derivative. Now, as usual, it's going to help if we can factor this as much as we can. So let's pull out any common factors, and it turns out you can pull out a 12, and you can also pull out an x. So if I factor out 12x, we're going to get x squared minus x minus 2. And then actually this can factor. X squared minus x minus 2, that factors as x minus 2, x plus 1. So really this is 12x, x minus 2, x plus 1. So with that in mind, now we've completely factored our derivative, which is nice. Why did we want to factor the derivative? Well, remember what I said our goal is? We want to figure out on which intervals I, and maybe I should just say it differently, on which intervals is f increasing and on which intervals is f decreasing. That's really what it would mean to answer this question. So in order to apply the increasing-decreasing test, we need to figure out on which intervals is the function's derivative positive and on which intervals is the function's derivative negative. Well, in order to answer that question, we're going to start by finding the places where the derivative is equal to 0. And that is actually what's going to allow us to answer the question. So really what we're looking for is critical numbers. That's how critical numbers are going to show up. We want to first start these questions by finding the critical numbers. So the fact that we've written our derivative and we've completely factored it, like you see here, that's a good start. So let's find the critical numbers. F prime of x is equal to 0 when? Well, when one of these three factors is equal to 0. So this one, this will be equal to 0 when x is negative 1. This will be equal to 0 when x is equal to 0. And this will be equal to 0 when x is equal to positive 2. So we can say that f prime of x is equal to 0 exactly when x is equal to either negative 1, 0, or positive 2. So those are your critical numbers. Of the function f. Okay, so that's where you want to start. And then what we're going to do now is we're going to draw a table that's going to help break everything down to figure out when f prime of x is less than 0 and when f prime of x is greater than 0. And you might help to think back to some of the inequalities we did in the very first section, because we're going to reuse and recycle a technique that we talked about then.